12th Science, Chapter 10, Haloalkanes and Haloarenes, Part 10, Reactions of Haloarenes. Hello students, I am Madhusina, your chemistry teacher. Watch my YouTube videos, like and subscribe it for further notifications. In this video, we will discuss about the chemical reactions of haloarenes. Haloarenes undergo three types of chemical reactions. They undergo nucleophilic substitution reaction, electrophilic substitution reaction, and reaction with metals. Let us discuss it in detail. The first one is nucleophilic substitution reaction. Haloarenes are extremely less reactive towards nucleophilic substitution reaction. Why it is less reactive towards nucleophilic substitution reaction? It is because of the following reasons. The very first reason is the resonance effect. Due to resonance effect, the carbon-halogen bond develops a partial double bond character, which is difficult to break. Let us see. This is haloarene having three alternate double bonds in benzene and halogen attached with 6 non-bonding electrons. One pair of this non-bonding electron goes on to form a bond here, so immediately the next bond will break and form a lone pair. So you will notice that by this, so double bond is being formed here. Halogen develops a positive charge because it is now deficient of an electron pair. Here the bond has broken, so form one lone pair and rest of the bonds are same. Now this is going to form a bond here, so immediately the next bond will break and form a lone pair. So a bond is formed here, lone pair is formed here, and the next bond is like this. Now again this lone pair goes on to form a bond, the bond breaks and forms a lone pair. So we are having X plus 2 pairs of non-bonding electrons. A bond is formed. Now the bond gets formed here and the lone pair on this side. Now again it goes on to form a bond and this bond breaks to form a lone pair. So we return back to our normal structure. The positive charge disappears because the lone pair is back on halogen. Now if you see these resonating structures, we notice that the carbon-halogen bond has developed partial double bond character. Hence, the CX bond cleavage in aryl halide is difficult as compared to alkyl halides. Secondly, there is difference in hybridization of the carbon atom. If you consider an alkyl halide, the carbon atom is sp3 hybridized. But in case of haloarene, the carbon atom here is sp2 hybridized. In case the halogen is forcefully removed, then the third factor which comes into picture is the instability of the phenyl cation. Instability of phenyl cation, which is being formed due to loss of halogen. So the probability of SN1 mechanism is ruled out. And fourthly, because of possible repulsion which is being faced by the nucleophile as it approaches, which contains more number of alkyl groups attached to doubly bonded carbon atom. Hence here 81% 2-pentene is obtained as the preferred product. Rich arenes. However, the nucleophilic substitution reaction takes place in case of haloarenes under drastic condition. The most common example is Dow's process for the manufacture of phenol from chlorobenzene. So from chlorobenzene, when treated with NaOH in acidic medium at a high temperature of 623 Kelvin and 300 atmospheric pressure, we get phenol. Secondly, haloarenes undergo electrophilic substitution reaction. But haloarenes undergo substitution reaction very slowly and requires even more drastic conditions as compared to those in benzene. Let us see why this happens. Due to resonance, the electron density increases at ortho and para position compared to meta position. Further, the halogen atom, because of -I effect, destabilizes the benzene ring as it withdraws electrons from the benzene ring. Hence, the electrophilic substitution reaction in haloarenes occurs slowly and requires more drastic conditions. However, some of the electrophilic substitution reaction undergone by haloarenes are as follows. For example, chlorobenzene. If we carry out chlorination Cl2 in presence of anhydrous FeCl3, this is chlorination. Now, from the resonating structure, we have seen that the ortho and para position, they are rich in electron. So, it gives us a mixture of both ortho and para products, out of which the para product is the major product because of the symmetry in its structure. Secondly, we can carry out nitration of chlorobenzene in presence of nitrating mixture, that is concentrated HNO3 and concentrated H2SO4. So NO2 group gets introduced at ortho and para position. Cl NO2 plus chlorobenzene at para position, out of which this para project is the major one. We can carry out sulfonation by heating in presence of concentrated H2SO4. So SO3H group gets introduced at ortho and para position. So this is 2-chlorobenzene sulfonic acid and 4-chlorobenzene sulfonic acid, out of which the para product is the major product. Chlorobenzene also undergoes Friedel-Crafts acylation and Friedel-Crafts alkylation. Let us see it. So Friedel-Crafts is basically associated with the use of anhydrous AlCl3. Friedel, Kraft. Alkylation means alkyl group is introduced in the benzene ring. So we can carry out this. Suppose we are taking methyl chloride in presence of anhydrous AlCl3. So here also what happens? The methyl group gets introduced in the benzene ring at ortho position as well as at the para position. The next one is Friedel-Crafts acylation, where acyl group is introduced in the benzene ring. For example, CH3COCl, acetyl chloride in presence of anhydrous AlCl3. So this acetyl group gets introduced in the benzene ring at ortho position and at the para position. So this para product is the major product. So this is 2-chloroacetophenone and 4-chloroacetophenone. Lastly, we have reaction of haloarenes with metals. In this, the first one is Wood's Fittig reaction. So Rx is the haloalkane in presence of 2 moles of sodium and an haloarene in dry ether. We are taking dry ether to absorb the traces of moisture. So 2 NaX get removed and R gets introduced in the benzene ring, giving rise to alkyl benzene. The next one is Fittig reaction. So here we are taking 2 moles of haloarene, treating with 2 moles of sodium atom in presence of dry ether. So basically 2 NaX. So here also we are getting 2 NaX. So basically 2 NaX goes out of the reaction and both the benzene ring join with each other, forming biphenyl. So this is biphenyl.